Hi everyone, my name is Changting and I'll be presenting on Chapter 20 about multiprocessing and vectorization. So why is multiprocessing and vectorization important in machine learning? Well, it's because the machine learning algorithms are computationally intensive. So to reduce training time of our algorithms, we need to write programs to run on multiple CPUs and on many servers. The first technique to speed up our program is called vectorization. It is also known as array programming, where an operation such as addition or multiplication is applied to a set of values. It replaces for loops with matrix algebra, compiled iterators, or generators. The advantages of vectorization are, first of all, it replaces slow nested for loops by fast iterators. Second, the code will be structured in a way to handle data of different dimensionality. So when we add a new dimension to the data, we do not have to add another for loop in our program. And last but not least, Python can run operations written in more performant compiled languages such as C or C++ under the hood. These languages are more performant than Python because many years of research has been devoted to optimize their compilers. An example where vectorization can improve the performance of our program is in Cartesian product. The Cartesian product is defined as the product of each dimension of the data. So in this example, we have a data with 3 dimensions. Each dimension has 50 elements. And in the for loop implementation, you can see that for each dimension, we need to write a for loop. Imagine this data having 100 dimensions. That means we'll be writing 100 for loop. Next, comparing to the vectorized implementation, it's much simpler. We can import the product function from the itertools library. And let's compare the performance of these two programs. So I ran them 5 times on my machine and take the average of the execution time. In the unvectorized implementation, where we use for loops, on average it takes about 48.6 seconds. In the vectorized implementation, however, it only takes 45.31 seconds. Next, we will talk about multiprocessing. But before getting into the details, I want to give an overview of HPC cluster, where HPC stands for High Performance Computing. In a typical HPC cluster, there will be hundreds or even thousands of servers. Each server will have multiple CPUs, and each CPU can have multiple threads. Between the servers, they are usually communicated over a local network, and these networks are usually have very high bandwidths. And the servers also share some storage. Typically, a few terabytes of storage space will be available. We're running our program on a HPC cluster. The first level of parallelization we can achieve is through multithreading. Each CPU has multiple processor or cores, and each core has multiple threads. So thread is the basic unit for computation, and operating systems can schedule multiple applications running on multiple threads. The advantage of multithreading is some tasks can proceed while others are waiting for slow operations such as input or output. For example, process A might be waiting for a response from a network call, which usually takes hundreds of milliseconds. In the meantime, the operating system can schedule process B to be running. That way, the CPU or processor is not waiting idle. But this can be problematic. Multiple applications might write to the same memory space. So Python uses a global interpreter lock to limit write access to one thread per core. The next level of parallelization is multiprocessing. It is done by running multiple tasks on multiple processors. Recall that each CPU can have multiple processors, and each processor will have its own memory space. So the problem with multi-threading, where multiple applications might be accessing the same memory, is eliminated. And Python has a library called multiprocessing for this purpose. So next we'll be visiting this multiprocessing library. But before getting into an example using this library, I want to share a few notes. When I was running the test program from Jupyter Notebook, I noticed it was hanging. And with some research, I found out the safest way to run a program using multiprocessing library is from the terminal. And second, methods of a class, which are called bounded methods, cannot be used as callback in the multiprocessing library. There is a workaround if we implement our own pickle and unpickle methods, but it's more complicated. And pickle and unpickle is a way to serialize and deserialize Python objects between different processors. Because multiprocessing libraries schedule tasks on different processors, it is necessary to serialize and deserialize our Python objects between the processors. And last but not least, the multiprocessing library can only use processors on your machine. It cannot send tasks to run on processor of a different server. In chapter 23 of the book, it will talk about how to communicate between different servers using MPI, which stands for Message Passing Interface. Multiprocessing can help us speed up simulation time. One such simulation is the one-touch double barrier algorithm. In this algorithm, we closest the position when the price either hits the upper bound or lower bound that is predefined. So here in the barrier touch function, we calculate the first time that such condition is met, the first time that the price hits the upper or lower bound of the barrier. The sequential implementation will run the simulation one by one on one processor. Next, comparing to the multiprocessing approach, the simulations are independent, so they can be divided and run on different processors, and the results will be combined. So does multiprocessing speed up our simulation? Well, here is a benchmark. Using random data points from 10,000 Gaussian processes. Each Gaussian process has 1,000 points. And running the same algorithm 5 times on a machine with 4 cores, we get, in the sequential version, it takes 56.89 seconds to run. But if we schedule the simulations on 2 processes, the speed improved to 15.04 seconds. If we use even more processes, it speeds up to 11.9 seconds. But when we increase to 8 processes, it actually takes longer. It takes 17.4 seconds. So we can see that more processes don't necessarily lead to better performance. In this case, the 8 processes simulation takes longer, probably because my machine only has 4 cores. So there is some overhead to schedule the 8 processes onto 4 cores. So from the benchmark, we can see that performance does improve with multiprocessing. So the next question is, how do we decide the number of jobs and size? How do we partition our data to run on multiple processors? Before going into that, we can define some terminologies. So atoms are indivisible tasks, such as a simple addition or multiplications. And molecules are collections of atoms that will be processed sequentially. So this could be a set of addition and multiplication that can be run independently on different processors. And the performance of our program will depend on how these atoms are partitioned into molecules. The naive way to partition would be linear partitioning. In linear partitioning, the number of molecules is the minimum of the number of processors and the number of atoms. Now, this is not the most efficient way to partition data when our computation has multiple nested loops, because the performance will depend on the heaviest molecule. The load is unbalanced. So while the processor with the heaviest molecule is finishing the computation, other processors are waiting idle. A better way to partition the data would be partition them into more molecules. So let's consider a two-dimension array where the outer loop iterates from I equals to 1 to n, and the inner loop ranges from j equals to 1 to I. In total, there will be n times n plus 1 divided by 2 operations. If the machine has n processors, we should divide the tasks by m, so there will be n times n plus 1 divided by 2 divided by m tasks. Now, some tasks might take longer to execute, but processors with faster tasks can take on more tasks. So in the end, the load are more spread out across processors. And here is the result of implementing such partitioning. You can see we have 20 tasks. Task 1 has the least amount of work, and task 20 has the most amount of work. These tasks are scheduled onto 6 processors, and in the end, the total amount of work will be more or less spread out across the processors, because the processor that takes task 1 will be taking more tasks versus the processor that takes task 20. This partitioning algorithm can be extended to work with higher dimension data. So in general, we want to divide our tasks such that it's not too small where the overhead of scheduling is impacting the performance. But we also don't want the tasks to be too big such that there are unbalanced workload between different processors. Now that we know the basics of multiprocessing, the author recommends developing our own generic library that can parallelize any kind of functions. And he called this a multiprocessing engine. In a multiprocessing engine, it will take a callback function that is the function to be executed in parallel. Then the engine will group the atoms into molecules of size that will balance the load across different processors. And last but not least, the function will also take a redux function to reduce the output on the fly. We already see what the first two means, so next we will cover what is a redux function. A redux function combines the result from each molecule. So for example, if we're building a sentiment analysis engine, we might need to know the word and its frequency of a text paragraph. So each molecule will be a paragraph, and each processor will compute the word and their frequency in that paragraph and returns the result in an array. If we have a huge text, we might have many paragraphs, and we don't want to store the result in a giant array. We want to process them as the result comes back. So the memory requirement for this program is smaller because we're not storing every result from every molecule. Before writing our own multiprocessing engine, there are a few things to consider. First, be aware of race condition. Memory can be read by multiple threads, but only one thread can be writing to the memory. If you have multiple threads reading and writing to the same memory at the same time, the result will be inconsistent and it will be hard to debug, which is the second point. Parallel programs are harder to debug because the order of operation is indeterministic. One thread might be running first in this run, but another thread might be running first in another run. So the result of operation is indeterministic, and as programmers, we have to take that into consideration. And if you have a sequential implementation, compare the result to make sure the parallel implementation and sequential implementation arrives the same result. And last but not least, parallelization is not free. There is a cost. So there is diminishing return in using more processes due to cost in scheduling or context switch. In the multiprocessing example, we saw that using 8 processors was taking longer than using 4 processors due to this kind of cost. To recap, in this chapter, we learned that some algorithms can be speed up through vectorization and multiprocessing. Vectorization replaces slow nested for loops with matrix algebra, compiled iterators, or generators. In multiprocessing, tasks are divided among multiple processors to achieve better performance. When implementing a multiprocessing engine, we should make sure that each processor does around the same amount of work. So when we partition the data, we should take that into account. And outputs should be reduced as results are returned to avoid post-processing taking too much memory. And in general, we should pay special care when writing parallel code. It can run faster, but at the cost of more complexity in our program. Thank you for listening to this presentation. Please leave feedback in the comment section. Thank you.